Hi everyone, it's 2 o'clock and thanks for joining us on this webinar entitled Get Cool with Conformal Cooling. My name is Dan Branch. I'm with the 3D Systems Software Customer Support and I'll serve as moderator for the event. We have several items on the agenda today. First, we want to just define what we mean by conformal cooling as it pertains to molds. So we're going to look at some different design principles and how they compare to more traditional cooling layouts. And then we have to discuss how conformal cooling channels are manufactured. And then, of course, we're going to look at the benefits that come from conformal cooling and see how they justify the process. We do expect that you'll have some questions as the webinar goes on. These you can type out to us. And at the end of the presentation, we will have a question and answer period. Any questions we can't get to during the time here, we will follow up with after the event. And you should know that the webinar is being recorded, so within a few days from now, we will email you a link to the recording here. Your speaker today is David Lindeman. Dave is an applications engineer for 3D Systems, specializing in the Cimatron CAD/CAM software product line, and has nearly 20 years of experience working with the Cimatron product, as well as field expertise in plastics engineering, injection mold design, and metal forming die design. So with that, I'm going to turn the floor over to David.
Well, thank you very much, Dan. Thank you to everyone else joining us this afternoon. We appreciate your time to take a look at this webinar. So just as an overview to give you a brief idea of 3D systems and what it's about, the slide shows how it's an end-to-end manufacturing system. So basically, if you can design it or if you can scan it, we can convert it into a CAD model. It can then be manufactured either using additive manufacturing, a 3D printer, or traditional methods such as using CNC machinery. That part can be expected and then compared again to the CAD model. So basically all things manufacturing can be accomplished by the tools that are available from 3D Systems. Today we're going to feature some of the capabilities of the 3D Systems direct metal printing. It's what makes possible conformal cooling and how we're going to apply that to injection molds. So that's part of the elements or ingredients of what we're going to discuss today. And we're going to feature some of the software available from the 3D Systems product line. Here you see it covers a wide gamut of disciplines in manufacturing pretty much across the board. We're going to focus on Cimatron, especially the mold design product, because that's, of course, what lends itself exactly to this application. Cimatron mold design has been around for many, many years. It's well proven in the industry. It's just continued to evolve as techniques and processes have evolved. Those things have been incorporated into it. So as we talk about conformal cooling, there's a lot more involved too with Cimatron mold design and the tools that are available for a designer so that he can quickly design a mold and do it in less time, even though it may be very complex and very large. All right, with that, let's get on to our subject of conformal cooling. I want this to be informative and to give you some good guidelines, not so much a sales presentation. So we're going to talk about what conformal cooling is, some simple definitions, ways that we can incorporate it, things that we need to do in order to have good guidelines for conformal cooling. Of course, we have to understand what's going on too when we print the metal core so that we get the best results. We need to know the nature of the printing process. We've got a couple of real-world examples we can look at that we'll mingle in and talk over a couple times just so we can highlight the importance of some principles they display. And the question for you is this for you? Is this something that fits? Is this something that you would possibly think about down the road for what you do? Well, what is conformal cooling? The simple definition is it's a cooling passageway which follows the shape, profile of a mold core or cavity. So as you see the shape, it wraps itself around it, essentially. And you compare that to what you're used to seeing in a traditional cooling line, such as this little example. It's formed by simple straight drill lines, and you can imagine that with those lines that go up into the core, that there's a baffle or bubbler directing the water along so that it'll flow into those areas. It goes toward the beefy areas where there's steel, but doesn't so much follow the shape that you see, which is the cylinder body. Comparing that to what a conformal cooling water line does, here you see there's one inlet and one outlet. It spirals its way up, crosses across the top, spirals its way back down. So its intent is to follow the shape and to capture as much of that shape and depth as it can. So in addition to calling it a cooling passageway, let's amplify that definition a little bit more and say it not only follows the shape, but its intent is to perform rapid and uniform cooling of both those things. We'd like to get the heat out quickly, but also all over at the same time as much as possible. And we'll illustrate why that's important, what the benefits of that are as we go through our presentation. Looking at an analysis that's done to compare standard cooling versus conformal cooling, here you see a simple part, and you can imagine the water is coming underneath the part on the blue side of the part. And while that helps greatly, you can see a lot of heat is still trapped in the details that are deeper within the core itself. Now comparing that would be a straight line drill passing underneath, the details of the mold. Comparing that to what you would see with a conformal cooling line, which could wrap its way up and closer into those details, you can see that the heat is being drawn out much more uniformly. It's not all red on one side, blue on the other. The heat's not trapped in the small details near as much as you saw before. And it's also quicker. So this analysis by MoldX 3D helps us to see immediately the benefits that can occur by adopting a conformal cooling system. Another way to look at it might be with this diagram. A simple straight drilled line like you see on the left-hand side. As you look at that, you can see there's three sweet spots that are close to the molded part itself. And you can see just because of its coming close and then drifting away to the corner, then coming back close again, that it's not going to be as uniform as what you see on the right, where you have a conformal cooling line wrapping itself around, keeping equal distance away. The conformal line is shorter in distance, and there are no dead spots. So all in all, you can see there's more engagement with the water line when you look at the conformal line versus the standard line. So the benefits are becoming fairly apparent. First of all, it can greatly reduce the cooling time. And as we get into some of the examples, we'll give you some real world numbers on that. But because it's uniformly drawing the heat out, it's going to reduce the warpage. Again, the round example from the slide before, it makes sense that the conformal line is going to give you a rounder part because it's pulling the heat away uniformly versus the other way. All this means improving quality and saving time on cycle time. A lot of places that are adapting conformal cooling aren't doing it just to save money on the cycle, but their customers are insisting a better quality part with less warpage. So those are two very key factors in terms of conformal cooling. And you might ask yourself immediately, anytime you're talking about reducing the cycle time, you're talking about lowering the overall piece part price. So does that justify the quantities of the part that are going to be made, being able to incorporate this system of cooling? Now that's not to say that we're not going to see some challenges when it comes to adapting to a conformal cooling line. As we've shown, you need to keep a constant offset from those mold faces, and ideally that would involve following a 3D trajectory like you see in the first example, or that easy one that we've already looked at. But the part geometry may not always make it so easy. Like the second example, you see in red, my water line needs to snake its way up and down and around, and based upon what you see here, it's not quite as uniform. So more thought would probably have to go into that in order to get a good conformal line. Versus the last one, which is difficult in that there's quite a bit more work involved invested in creating that conformal cooling line. You can imagine where you see it going up and down over that cylindrical area. That area has been sectioned through different planes, and those planes have been used to guide the direction of that water line as it goes back and forth. Kind of illustrates a bit of a trap too, in that once you get down and into that part, you can make a much longer line than perhaps you intended. And we get back to the idea of uniformly drawing the heat away. Sometimes it's better to break that up as opposed to creating long water lines. So there's some principles already shown here just in these few examples. So let's step our way through some basic guidelines. All right, like the first one we talked about, follow the shape. Stay a uniform distance around the geometry that you're cooling. And that's not just in a 2D planar view, but also for any 3D. Like you see here with the water line curling underneath the part, I want to keep an even 3D distant offset away from that part, like you see here. So as I build up water lines, I may see something like this. There at first looks like maybe that was intersected by planes. Maybe the faces were offset so they could hold the distance, and based on that intersection, I found exactly where the center of those water lines should go. But in the profile view, you see how that water line is drifted down a little bit. We want to keep it equal distant, 3D, away from the part, and equally distributed as it works its way around the part. All right. So there's some design considerations there to look at. Now, looking at the water line itself, one of the key ingredients is to keep the cross-section of that water line uniform. So maybe I'll change the shape of it as I direct it around certain mold details. Like in this example, maybe I would go from a round diameter and need to squish it sideways to get between a couple of ejector pins. If I do that, I also need to elongate it so that I maintain that constant 2D area of the cross-section. That becomes important so that the same amount of volume of water is going through that water line. And that's true no matter what shape I use when it comes to that section. We'll illustrate that further with another example. Then the type of shape needs to be considered. For instance, you see the square, and we put a big red X on it to illustrate the point here. This has to involve the way the 3D printer operates and understanding the nature of the printing. We X out that square because it's flat across the top, which means it has a large overhanging face. As the part is built up, as the core is built, it's basically powder that gets lasered, and that is built layer by layer. So in the middle, as that water line grows, you have material forming around it, metal forming around it, but the inside of that water line is nothing but powder. So now I reach a point when I come to the very top, I have to go all the way across it with nothing but powder supporting it. And that can cause the water line to not come out to the shape you desired, right? So you see in the other options, the doghouse shape, or perhaps taking that square and rotating it more to a diamond shape so that you can slowly build up the sides as they come together to the top. Those are called overhanging faces, and that's one of the key importance of understanding what's involved when it comes to printing these water lines. And then you got some basic guidelines that I'm sure you already know if you've been designing a mold. One is to keep it a legal water path. You want the water to come in one direction, you want it to come out another direction. You don't want the water to divert, meander, and then come back because you can't control how much it may go on one side or the other. You don't want the water to loop itself. You know, there's basic things that you probably already have in mind when it comes to water when you sit down to design a mold. A lot of people, when they first start, wonder what size do I choose of water line? How big? What shape? There's a lot of questions and uncertainty. A lot of the times you can just start with what you know. If you've been doing molds and been drilling a 7/16 diameter drill line, start with that. You have rules, no doubt, about how far away you want that water line from a mold insert or from the face of a mold, or how far apart you want your water lines to be from one another. That's a nice starting point. that you can use, and stick to those rules as you start building your water lines. And with that comes the importance of being able to analyze what you've done. So now you can tweak it. Now maybe if you do move them closer together, you'll get more heat drawn away from the part. Or maybe you're too close. There's a lot of ways that you can analyze this using a product like Moldex 3D that's going to help you to see if your water line is doing what you want. Importantly, you want that analysis to know that you are uniformly drawing the heat away. And then you're going to get a better quality part, as well as it calculating for you the cooling cycle time. So with those basic guidelines in mind, let's take a look at a couple of examples that we have here. These have been printed and some have gone right to production. The last one actually made parts, so that's a real good example that we can consider. And in this case, you can see it's a fairly complicated water circuit shown there on the right-hand side. It actually has two circuits, one shown in the purple and the other in the blue. We'll dissect that a little bit and talk about what it took to make that type of conformal cooling line. First of all, the numbers, as you can see, by going from a traditional cooling pattern to the one shown, it took a good 20 seconds off the overall cooling time, improving the efficiency quite a bit. Plus, it also took away quite a bit of the warpage, improving that reducing the warpage by 20%. And you can see the two pictures showing you that one on the left, it's much more uniform versus heat being trapped on the one on the right. To do this, it took a little bit of work. And here in the diagram, you see different shapes that were used to create this conformal cooling line. A lot of that has to do with the very tight area that it fit up into the deepest part of the core, which look like those standing blades at the top part of the cooling circuit. Those were created by offsetting the faces, a constant value, and then doing what needed to be done, whether it was trimming it, using surfacing, or shelling it using a solid modeling function. The important thing is that those faces were kept a constant offset away from the mold face. Then the circuit had to be built to bring the water up to it, flow it over the top, and bring it back down. So if you look at it, you can see the dark purple at the bottom is the inlet, where the water is fed in. It shoots up through the lighter purple, goes all the way to the top, comes back down, and is exhausted out the center with another big ring inlet. The blue is very similar. You'll see in the blue, it's brought in and then brought to that ring where it's diverted off into capillaries. And each of those capillaries meanders around. There's some areas, if you look closely, it looks like they've been pinched together, which would be going from that round shape to that more elongated rectangular shape. And that's so it can fit between a couple of different mold components. The important thing is the cross-sectional area remained the same throughout all those different shapes that you're looking at. So the flow of water was even all the way through the water circuit. So there's a bit of work involved in that. And it took a while to develop that. So you can see that there's the need to be able to use constant offset from the faces and follow a 3D trajectory as we build this sort of water line. We need to be able to change the shape of the water line from time to time. But we do this knowing that there are going to be certain limitations involved when it comes to printing. One is no hanging geometry or no flat tops across it. So the object shapes that you see with the red X are ones that are not good for printing because there's too wide a horizontal area along the top of it. Whereas the other shapes, the one in green, give you a much better chance at printing it fully because there's less overhang. And another good rule here is to keep your corners round. We recommend 1 millimeter on each of the corners so that there's no sharp corners to any of these water lines. So what did it take in terms of software capability to model this? This water line used every bit of the tools available in most CAD modelers, being able to use wireframe in order to direct the flow of that water line, much like a pipe command, we had to offset surfaces and use different solid functionalities in order to create the geometry that would make this water line. We also needed a dedicated tool to analyze it to make sure the flow was what we thought it would be and the results would be what we needed in mind. So that meant some dedicated design functions, which we can't stress the importance of. Being able to 3D offset surfaces without the faces corrupting and falling apart, without all the work of going in there, needlessly trimming or whatever, replacing faces, a good offset, whether a shell, whatever command that is, that's within the CAD system is important. We might think of a circular water line following a trajectory being something like a 3D pipe command. All right, and the idea behind that is not just to be able to flow a circular shape, but to be able to do that with a non-circular shape, which could be anything, a star, anything. To do that without it kinking and bending and failing. So the thought of a pipe command may come to mind when you're thinking about running those water lines around. If we take that one step further, we could think of something that we might replace a pipe command with or augment it with called a conformal cooling line. So instead of just piping it, you're changing the shape as you go and transitioning it, redirecting it, perhaps even twisting it, doing all these things in one function. So the ideal thing would be to be able to do the conformal cooling with an actual functionality created just for that type of geometry. So looking at the part here that's been printed here, we'll show you just a few slides so that you can see what it looked like after it was printed. There on the right-hand side, the upper right corner, you can see what the part looked like while it's still sitting on the mounting plate. From there, it needed to be cut off, so it looks like the one on the left-hand side. Okay. Also, you can get an idea of how big this part was. A couple different versions of it, a couple different designs of it were printed here, as well as the plastic one, so you could look into it and look at those water lines. It went a little further, they actually printed out the water line as an object, so that you can see it here, as well as a larger full-scale plastic one. Okay, so there's a bit involved in testing this product out, testing this part out, and getting examples that we can communicate with. So again, your overall sizes, what it would look like. There was the core shown on the left, the internal water line, all its complexity in the middle, and an overlay at the very end. So you can appreciate the design time involved. So a little bit about the printing of this. So each of the layers of these prints went from 20 to 50 micron. You might find typically metals printed in a range of 30 to 60 microns, so it's right in that area. It depends upon the capabilities of the machine, design intent, the degree of accuracy that's wanted. When this part was printed, the machine available would allow for a 2 millimeter pipe, 2 millimeter diameter pipe. And again, we have to think about the top of that shape, being able to support it while it's being printed. Newer printers can accommodate up to an 8 millimeter round. So as the technology continues to progress, it's becoming more and more easier, I guess, in working with the different shapes and sizes. Also, we had to limit ourselves to a negative draft angle of about 45 degrees, so we couldn't get the angle at the top any broader than that. 45 or less was what we needed to be able to support a layer on top of a layer as the print drew in closer to the center. Newer printers can get up to 20 degrees, which is a vast improvement. So here you see the statement of the accuracy as typical of all printers. It's pretty much the center is the most accurate location for printing. So typically with a core cavity, we'll put it dead center on the tray. That's where we'll print it at. And as it goes further and further away from the center, we lose a little bit of accuracy. Plus the surface roughness, that's something of concern to everyone, or something to take note. As we build up layer by layer, that does incur a pattern in roughness. Basically, you think of lasering the powder. It goes through a shrinkage. It lays the next layer of powder. It also shrinks. So you will see this layering effect. And that's going to be whatever the layer size is that you're printing at, 20, 30 micron, whatever the case may be. Then if we get into an area that's angled, you're going to see more of a stair step on that, just like you would if you were cutting with an NC cutter, an end mill. You know, like a flat end mill is going to leave a little teeny tiny corner as you step it down layer by layer in the Z-level roughing routine. But what about the inside of the cooling channels? Is that of concern if it's rough like that? No, not at all. In fact, it's actually desirable because the roughness of the print itself lends itself to creating more turbulence, which is going to be helpful in drawing the heat out. So we raised a bunch of questions. What's the best shape? Well, the thing that's best is whatever you can print, first of all. And also, we look at the effect of that shape in terms of how good it is at drawing heat away. And we have found that the circle is actually one of the least effective shapes, even though you might think that's like one of the easiest to work with. That's because it has a minimal amount of surface area to work with as it pulls the heat away. So the shapes on the left-hand side, well, perhaps the most printable are what you might consider the lower priority in terms of heat. Whereas on the right-hand side, you can get more heat because of those shapes, but the caution is to make sure that you don't have wide horizontal areas across the top, because those will become overhanging. Now, one of the ways of defeating that is by rotating that shape into a more printer-friendly direction or twisting it as you wrap it around and spiral it up through the core that you're working with. We'll talk further about this. We found some numbers that we can throw at you that you will probably find very interesting. So let's look at these shapes, all right? The important thing to remember with looking at all this as we go shape by shape here is to know that the 2D area through that shape, the cross-sectional area of all of these in these calculations is 0.15 square inches, every one of them. But what's important to know is how it changes that perimeter. So in a round, perhaps a 7/16 drill line or round, I'm going to get 1.374 on my perimeter. That's the area I'm working with, the surface area, to draw the heat. As I change that to a square, you can see that I get better surface ratio surface ratio, and that area has increased. So the perimeter is much larger, but the problem is the flat top, as we discussed. Solve that by rotating it. Now I've got a diamond shape that will work nicely. Now going further, maybe take that over into a triangular shape. Again, you can see there's a much more conformal surface area, or the perimeter has increased while maintaining, again, 0.15 square inches cross-section. As we've worked with printers, I've had the chance to talk to some people that have been metal printing for years now, and they made a comment to me I thought was pretty interesting about the teardrop shape. He said the teardrop shape came around because they first tried to print around, and this is actually kind of how it came out. You know, the horizontal has got flatter and flatter across the top. It's harder and harder to print. So that's actually more the shape that they were seeing when they would cut the part open. So why not use it? So using the teardrop shape, they find that they get good build characteristics. It's one of the best that you can print. And it does a pretty good job when it comes to the conformal surface area. You may not see the big perimeter number like you would in other shapes, but you got one of the best printable shapes. Now you can help yourself greatly by this. By taking that teardrop shape and rotating it so one of the flat sides of it is parallel to the outer mold wall. All right, so that flat side is going to do much more work being parallel. It gives you a more of a conformal effect, a more constant distance from the part, and that helps to maintain that flow volume because it's a good shape. So the perimeter, you're getting the most out of it, even though the number on the perimeter may seem to be a smaller number. Going further would be to take what we've learned from the shapes and say, let's make it a triangular section, use the best available with that, plus kind of keep it close to a teardrop shape, tip that wall over so it's close to parallel to the mold section, and here you get a nice result. You can see the perimeter is bigger, but you also get that accentuated conformal effect. So a lot of times these shapes are going to be the best because they're easy to print. You can get it into an area. They wind around nicely. They blend nicely to other shapes, and you get that good sidewall effect with that wall being parallel to a mold face. All right, so this gets us back to software and having a dedicated tool designed just for the creation of these type of water lines. So I'm going to show you what Symmetry has to offer here with a conformal cooling water line function. Here it's a matter of picking one of the more popular types of cross sections, or it could be a cross section of your own choosing, giving it the size, and it will give you the calculation for the 2D cross-sectional area that you're working with. In this case, the wireframe curvature around the part was created just by offsetting it. And I'm using that as a guide as I pick my way around. And as I do that, you can see that shape is developing. Then we may choose to pick a different shape, put our values in. So again, we're even when it comes to the cross-sectional area. And then continue working. Maybe in this case too, we'll also tip it at a few degrees. And so it's a matter of what your preference is, but you can see the flexibility here. So it transitions from shape and continues to wind its way around. So those are some of the tools available that you see within this conformal cooling line. Now that's not to say that's the only thing, however. So what we'll do on this little movie clip here is jump back into it. A lot of times maybe the water line shape is going to be constant, and I'm not worrying about transitioning from shape to shape. In this case, I might like a shape that I can drive along that sidewall, or maybe I'm thinking of something for turbulence, so I use that X shape. So it's just a matter of chaining that, and it will drive that shape all the way around and through. But for the sake of turbulence, we can do something else, and that's twist it like a piece of licorice. So that will create the turbulent effect as it flows through that water. Maybe I'll transition it as I loop it down into the lower water line, but all those tools are available. Plus, there's a visual analysis that can allow you to check to make sure that that water line is staying a safe distance away from an ejector pin or a screw hole, or whatever the case may be. So it's checking as it goes. So let's talk now about what we need to do after we've printed it. We showed you that you need to take the part off the mounting plate. Typically that's done just by mounting it up on a wire EDM and wire cutting it. That's the simplest way. It's very unlikely that you would have any external supports when building a core cavity. That's because it comes down to a flat bottom on a mounting plate, and there's nothing hanging out over the sides like some other printed models that would need external supports. But we do need to have enough material around the part so that we can do a finish milling operation. We're not going to go back in and clean up the conformal cooling water lines. We like the roughness from the print, keep it the way it is. We have to have material around it so that we can finish machine it. That's the same as this diagram shows you here. So that you get the idea that it's a 3D offset done around the fit areas of the part, as well as what I want to have is a good clean finish for my molded surfaces. Okay, so that will require a post-printing operation involving my CNC machines. So a comparison now of operation per operation here between the way we'd go about doing it the standard way versus printing it is shown here. You can see that printing will replace getting the stock together, doing any of our roughing, even quite a bit of our NC drilling. Maybe we'll drill a little bit to get a good clean entry and exit where we're going to tap it and put our pipe tap fitting. But from there, the process is much the same. We'll still need to heat treat it. We'll need to do any finish grinding or any finish milling. And then if we do have a case where it's a long, deep rib that I cannot finish with an NC machine, I'll probably still create that same electrode to get down there and burn it. So let's go into another case study. This involves a simpler part, and as you see the picture, you can see this is one of those teardrop shapes that winds itself around the inside and follows the outside shape of the core. And then looking at the cavity side, here you can see it in the diagram shown in the software. So in this picture, I want you to take note of that unique little pattern. You see it looks like diamond shapes coming from the sides, that infill pattern. One of the things that the printing process gives you is the ability to do these infills where you're not putting printed material in an area that's of no real effect. So you can minimize and reduce the cost of the machine time, the cost that goes into the printed material by doing this sort of an infill pattern. That depends upon what you're doing, right? You know, what the mold is and what that area of the mold is going to experience, right? In this case, this project was done in Cimatron using a mold design function, so not just the conformal cooling function, but all the different mold design capabilities that Cimatron has, and it allowed itself to rapidly design the part and get it ready for more of a conformal cooling process. And then, again, 3D Moldex was used to do the simulations to prove it out before we committed to printing the steel. And here's how they went about doing it. Again, you see the teardrop on the inside of the core, as it was shown on the cavity as well. The idea is to keep that outer side parallel to the outer surface of the part, running around kind of a tapered helical effect, and that resulted in the results you see below. The core ran consistently 12 degrees cooler and also reduced the cycle time by 13 seconds. So those are some pretty important considerations there, just because of the design. Using this example, here we have a dollar by dollar comparison, doing it the conventional way versus using conformal. So the first line design, dropping from 30 hours to 7 hours, isn't just because of creating conformal cooling lines, it's because of switching from one design system to Cimatron and using its mold design system along with the conformal cooling functions that you saw. So you see the resultant savings there. Of course, the programming and machining time is going to be greatly reduced because there's far less involved in that. However, you see the material and the additive manufacturing build time, taking a block, squaring it up conventionally, $350 versus what you see here in order to print that. Okay, so that's where the cost came involved in the conformal cooling design. EDM time completely disappeared, and then polishing time just increased a bit when it came to finishing up the outside of it. What's important is you see they were able to print the core and complete the post-printing operations and still save $2,500 on each core. What's not shown here in the diagram is going to be the return time. To say you break a core for some reason and now you need to replace it. It's far less time consuming to print it, machine it, harden it, do what you do then to do it the conventional method. So that mold could be back up in production quite a bit quicker by replacing it with a printed core. Also, let's look at how that affected the molded part. Here the mold is run at the same temperature, but you can see there is quite a difference in the overall cooling time as well as the overall cycle. So the cycle time reduced by 14%, which means it's more cost effective to manufacture that part using a conformal cooling mold. Plus, looking at the quality, we know that part's going to come out rounder because it's going to pull the heat away much more uniformly. So per this job, the summary we could come up with is we saw a mold design reduction of something like 75%. The EDM work pretty much disappeared from it. There was far less time programming it and generating in CPath and running it on the CNC machines. And that meant I was less reliant on my mold maker. That means I can take my skilled mold maker and kind of spread him out across more work and use him more effectively than perhaps the traditional method. And I bring this up because it seems talking with mold makers, it's harder and harder to find skilled, experienced, quality mold makers. So to be able to get the good use out of them that benefits the shop and themselves as something to consider. Plus, again, significantly faster turnaround when it comes to making and or replacing components. So that brings us to our end here. We've considered quite a bit. Hopefully you've explained what they are calling conformal cooling and what that means. We're taking a cooling passage, we're following the shape of it, and the idea behind that is to, as much as possible, uniformly and quickly pull the heat away. We've seen how it compares to the traditional process of drilling straight drill lines versus wrapping that conformal line around to follow the shape. We realized, too, to accomplish this, we are going to need to use a 3D metal printer. And to our benefit, we should use the softwares to help us create it more effectively and check it to know that we're getting the effect we want from it. What are the benefits? Shorter cycle time, quicker turnaround on the tooling, also better quality of our molded parts. So thank you very much. With that, let's give our attention back to our moderator, Dan, and he can go over any questions you may have.
Okay, thank you, David. We do have a few questions, which we'll start with, but I'd like to remind everyone that if you've thought of one while the presentation's been going on, just to type in our Q&A area here in the webinar screen. The one I'm going to give you first, Dave, I think is one that a lot of people may have thought about, and it has to do with the quality of these printed cores. So how long is a printed core expected to last as compared to a conventional core?
Gotcha. I can't say from firsthand experience, but I have been told that you could expect to have the same life from that as you would a conventional. So if you're expecting 1 million shots per cavity, then that's what you can expect from a well-done printed core. I mean, you're going to print it, you're still going to harden it, you can do anything else you would do with that core like a conventional core, grind it, machine it, weld it, do all those things. So it holds the properties, the characteristics, and I'm being told that you should be able to expect the full life, typically 1 million shots per cavity.
Yeah, I know the quality of the cores I've seen printed were amazing. It's not like they used to look. Very pure material. So
yeah.
Next question is probably...
I was going to say, some are saying they're getting 99.9% density, which is, that's incredible.
Hey, here's a quick one for you, just about the printing process itself. The support material, is that the same as the build powder?
Yes, it is. There's only one material allowed per run when it comes to printing materials, printing metals, I'm sorry. So anything you build as a support will come from that material, from the powder.
Here's another one for you, and about the design. So when twisting the cooling channel to get the more turbulent flow, how do you avoid a hangover situation when the flat side rotates to the horizontal?
That's an excellent question, and that takes consideration. Like star shape, there was a while it seems like everyone was really intrigued by that star shape, but there's a point when you rotate that, if you keep twisting it, those two flat areas will appear. So the idea is you twist it, keep twisting it, now you've minimized the overall flat areas across the whole water line, but you still would need to understand those areas where it may occur and see if that's something that's critical or not. Can your printer do that width? Some can, some may not be able to. So that's the concern.
Sure. Next question for you. Could you tell us more about the heat treating process of the cores and perhaps some specifics on how hard the material can actually get?
It's from what I'm being told, the heat treat process is the same as far as time, the amount of hardness that you desire to achieve. Some of the steels, the tooling steels printed have been compared to T20. Some have been compared to an H13. And as far as the process goes, it would be the same for those two materials. So that's about as much as I can tell you, other than when you get it back at that hardness, you're going to have to machine it the same as you would a conventional core, hard milling it.
Yeah, being as a result is so pure and basically like a machine core, I suppose the heat treat and hardness would be very similar too. We have lots of questions coming in, Dave. I'm going to slip in this one that's very similar to the last one, and that is, what are the limitations when working with a printed core? And I think they mean what sort of machining processes are you going to be able to use on that core after it's printed?
Well, you can again grind it, weld it, harden it, machine it, hard mill it. There really EDM it. There really aren't a lot of restrictions other than what you might think of when you're doing it regularly. You know. So offhand, like the examples I showed you, I can't think of too many. You know, really can't think of any when it comes to creating an injection mold core.
Sure.
You can plate it too. You can polish it. You can do all those things as well.
Right. Here's one that goes back to a slide just a little bit ago about your overall benefits. And the question is about how you calculated the design time reduction. Wouldn't tool design still remain a constant? Because I'm still designing the mold, whether it's conformal or traditional cooling cycle.
It would. In the example I showed, we switched from one design package to another. So we went from a more conventional CAD/CAM sort of package that has limited mold capability to Cimatron, which has dedicated mold functions, not just the conformal cooling one, but also other things like automating the ejector pin trims and locations and putting in other things, you know, other components and automatically giving you your fit pockets and all that. So it's not true apples to apples, and that it was actually one design system compared to the other being Cimatron.
I see. So the next question I'm going to actually refer to offline. It's about just getting a look at how these 3D metal printers work, which we're not really able to do in this session, but there are videos that we can link to you.
Okay, yeah.
And so let's move to the next one. And we may have touched on this. The printed core, what does it most closely represent with regards to steel? And the question is H13, stainless, etc. Maybe a mention of the powders that are available.
Yeah, I know you can print in stainless steel, aluminum, titanium, tool steels, like that. Those are the ones I've seen working with. And so that's about as limited as what knowledge I can give you on that.
Mm-hmm. Yeah, and definitely at this day and age, there's very little difference between the printed core and a billet part at this point. Next question is, let's say you make a change to the part that interferes with the conformal cooling channel. How would you go about fixing?
That's a good question. Well, I would go back to my design, and I have to go ahead and make that change and then interrogate it. I can run the function on the cooling channel that shows me if I'm within a safety range. I mean, if I hit it, that's a collision, that's one thing. But I want to have the same amount of material all the way through and know I'm passing that test, so the water line is uniformly distant away from the mold. So there's a check that you can run to see if it's maintaining that. And if it doesn't, then I will have to go in and edit that, you know, make whatever changes and how I control the size of it, you know, so that gets into redesigning it at that point. Or if it's a parametric entity, I might be able to change that dimension a bit, draw it in closer to the center of the core, perhaps, you know, something like that. And it's going to vary by, you know, job to job and complexity. The change may be such that I would have to completely redesign an area to avoid a whole new feature, you know, so it could be more involved or it could be a little more directly involved. Important thing is I can use the software to check to see where it hits, where it doesn't, or where it's not safe anymore.
Right, and as far as the repair on the actual core, I'd say that your options are very similar to any other core block, correct?
Yeah, exactly.
What would be your recommended cleaning procedure or water filtering for conformal cooling channels? So given that they twist around so much, this is about removing potential sediment, scale, etc.
Right. Well, if you can get away with regular cold water, that's great. I've heard some talk about using distilled water so that there's no impurities in it. I'm not sure that that's like totally necessary. You know, if you're using fairly standard size water lines, you should have enough good flow going through it. You know, just keeping it clean conventional ways, probably pretty good. So far, I haven't read anything about it where there's been a major concern. More like the designer is more worried about it when he starts making real small capillaries, if that water is going to get through. If anything, the concern is more like, if I get too crazy, am I going to be able to shake all the powder out of it more than anything?
Right.
So, that's more of a bigger concern right there than initially the water itself.
Okay. There's and by the way, everyone, I thank you for the good questions. We've got a few more coming in here, Dave, so we've got plenty to talk about. Or can a printed core have a texture put on it, acid etching, that kind of thing?
As far as I know, yes, it can. I've been told, I can throw this in there too, that we can get a Class B surface finish on a printed core, which is pretty good for most molds. Maybe not, ones are coring Class A, but it seems that we can do most of that and certainly acid etch it too, from what I've heard.
Are you saying straight out of the printer or with some post-processing?
You have to post-process that.
Okay.
Straight out of the printer, you won't have that, no.
Any opinion on how close a conformal cooling line can be to the part surface?
That's a good one. It all depends on the shape. It also depends on how small that water line is. There's no set rule that I've seen on it. There's an area of safety that I have in my mind from the times, I've done molds, and I want to keep it at what I consider a safe, comfortable distance, so I've got good material there, So I've seen people say things like maybe a diameter and a half min-distance. Maybe when it comes to like shooting a water line around a core insert, about the same, maybe a diameter's distance, or some just say no, nothing less than half of an inch. Some say if you're going to come within like a bigger mold, stay a good 2 inches away. So I wish I could give you a more definitive example, but it's varies from shop to shop, just like water lines done conventionally are varying from shop to shop in many occasions.
Sure. We're definitely going through some thermal cycles there, and metal being metal, there are chances for cracks, et cetera. So.
Yeah.
What about the machining aspect of it? One of the slides recently was about leaving some stock on, and the question is, how much stock would you recommend leaving on before machining the part?
Oh, the last one I printed, we left 30 thousandths on it all the way around. It seemed to clean up pretty nicely. So that was that's the plain kind of maraging steel. So being printed at about 30 micron per pass, so that seemed to do pretty well. That's just like maybe a middle of the road number. I don't really want to go. I don't want to go bigger than I have to because it costs to print it, But I want to have enough to clean it up. So I think after a while, experience will get you closer to that number.
Okay. This is a powder question. I'm not sure we know all of the ones that are available right now, but is there a powder material available like a P20 that does not require any hardening afterwards?
I don't know. There's something similar to P20, but I'm not sure if it goes that far.
Sure.
Good question.
Okay, so we'll try to get an answer on that one. What about warpage? Is that a concern when 3D printing these cores?
There is an effect that takes place. You're hitting the powder with the laser, and there is a set shrinkage factor that does occur. And as you build it up layer by layer, a stress can be built into it. Typically, with something like a core, the warpage is not extreme. Especially if you're leaving material on it, so you're going to clean up, finish machine it. It's usually fine, and it's stress relieved, right? If you get into a crazy part that's all twisty and bendy and it's supported, kind of flimsily, then warpage is more of a factor. You might think of some organic design for a consumer part. That'd be more of a factor than what we're doing with tooling.
As a Cimatron guy myself, I like this next question. Can you speak more about the design software for the water channels? What are the advantages over traditional 3D modeling software?
Well, Cimatron has the ability to do like the conventional water circuits. So basically, if you place in something like a baffle, it will let you dictate how far you want to drive it. It will check the length of the baffle to make sure it's not hitting or staying a safe distance away from the mold face or any neighboring component. And that's true also with all the waterline functions. If you were just to draw the shape of the waterline, whatever pattern you want, it'll check against everything. With the conformal, it will also check against everything. So once you got an idea of what you want your water circuit to look like with the components, you can run a quick analysis to make sure everything is legal. You know, you're not going into a dead spot or looping or, you know, some crazy thing like that. And then that information can be fairly automatically grabbed so that you can run an analysis on it. And it'll give you your, you know, it'll calculate through the injection time, the cooling time, if you use an analysis software like, say, Moldex 3D. So it partners with that pretty nicely.
Cool. We do have a couple more here, Dave, and I thank everybody for hanging out with us and for the good questions. The next one I want to ask you is about doing a project with conformal cooling. If a metal printer is not available, or maybe they're not comfortable with running out and purchasing one of these machines, do they have options that are available to start toying with this?
Yeah, in fact, we offer a service called Quick Parts. You could send that to Quick Parts. You could probably Google them and look at the 3D Systems website to find them, and they'll give you the quote. It's, you know, print it up for you. They have a number of different manufacturing things they can do too besides printing. So you can talk to them about what else you might need done to that printed core, whatever the case may be. But that service is available, and that could be a nice entry into it if you wanted to, or if the need were placed upon you to create a mold with conformal cooling. But you know, if that's like the one you're going to do this year, you may not feel like running out and getting a 3D printer and learning how to run all that stuff, right? So that might be a nice entryway of beginning it, you know, and getting your feet wet.
I think the next one is a tricky question, but I'll ask it anyway. Can a printed core be made of two materials? Let's say mold max or copper base is a primary, but can still be used in shut-off areas.
I don't believe so, unless you design it as two components. Which
kind of print them and assemble them.
Yeah, my experience has been to print with one material, and I feel like I have not seen a printer that does multiple metals.
Yeah.
And you realize what you're really doing is you're taking powder and you're welding it together. So you can see why one material at a time, you know, one material per run is pretty important.
Sure, sure. The process itself pretty much lends it to the material in the machine.
Yeah.
I can tell the next question is someone who was watching your show and was kind of thinking outside the box here. Could you design irregularly shaped vents in your cores with Cimatron?
Can you design irregularly shaped vents?
Yeah, probably looking at the flow of the conformal cooling and seeing, maybe we could use that for other things. So.
I don't see why not. You could. And it's not just with the conformal cooling function, but there are a lot of other nice modeling tools that you could use. So it's a very robust wireframe surface, solid modeler. It's all hybrid in that, you know, everything works in unison. So it's not like you have to jump in and out of different environments, anything like that. But a surface is a face, is solid, is the edges, like a wireframe. It's all very friendly and hybrid, I guess is the best way to say it.
What can you say about any special, this person's being specific, EPA considerations or other requirements to bring metal printing equipment into a shop environment?
What little I know of that doesn't have so much a shop environment as much as it is a medical facility. And depending upon that shop is part of the medical facility, I guess, you know, there can be extensive EPA requirements. The idea is that they want the process to be so well documented that it's almost impossible to vary from it, including, you know, how your procedures on loading materials, the templates you use when printing, we call them a build style internally with what we have. So you're going to use that same build style again and again. That has to be documented. It depends, but my experience isn't so much just for shops as much as it is what a medical facility. In a lot of cases, they're actually direct printing metal parts that go as inserts, for bone growth or something like that. So I know that's strenuous. That you can't do any shortcuts to. They have to have it all well documented. As far as tooling, I'm not so sure. I guess it depends on how deeply they're involved in it, and what their customers, if they're an outside shop, what their customers are insisting they be able to provide for their benefit. So I can't give you any more of a answer that's less vague than that.
I think I might add on myself, just based on what little experience I've had with these machines here in the company. And the first thing we talked about is safety. Like any other large piece of shop equipment, but these metal powders are very fine. There is a flammability possibility. And let's not forget, too, that there's a shielding gas kind of inside these machines. They're a sealed environment. So there are a couple of hazards and safety things that are the first things you learn about when you start dealing with these machines. The next question, I think, has been alluded to a few times, but this person's just coming right out and asking it in a very plain way. Can you print by adding on to an existing core or base plate?
Well, essentially, every print starts with a base plate, and you're printing onto it, whether it's a core or whatever. So the effectiveness of that I would be unsure of, depending upon the geometry, but I can tell you that your base plate is just basically a plate of steel that you start with, and then you start putting powder on it, start welding it up, basically, or start using the laser to build it, and it grows from there.
Yeah, I think the only real issue would be making sure you know where, if there's existing geometry, it's not a flat plate, then you, of course, have to cite that in and know exactly where you're at.
Sure.
Yeah. Do conformal cooling lines require special pumps? This would be at the molding machine, due to increased pressure requirements.
I haven't run into that yet, but most of the water lines I've seen have tried to emulate standard sizes, if for no other reason, so that we can use the same pipe fittings, just by drilling it and tapping it. So I haven't seen a difference in pumps yet, as far as that goes.
Sure. Maybe we could do a little offline and check into that. Are there any important characteristics you consider when choosing the powder for the job?
I'm not so good at understanding all the materials per se, but a couple options we've seen are the P20 similar grade, the H13 grade. I know those are available. Anything beyond that is going to be the requirement of the tool. I can't imagine printing a stainless steel core unless I'm really involved in, something specific to the needs of stainless steel or aluminum. So
right.
I can't
Similar
think that
the decision you'd take without printing, what material suits the job.
Exactly right.
We're about at the end here, everyone. There's a question. This is about the corrosion in the cooling channels also. And I think that was one we decided we weren't too sure about. But Dave, do you know of any difference when using a powder printing technique, conformal cooling, versus vacuum abrasing? And can you speak to any advantages, disadvantages?
I'm afraid I don't. That'd be a nice one to do some research on.
Yes. Hopefully allow us to get back with you on that. And that does take us to the end of the questions, 28 of them. That was a nice group of questions. So thank you all very much for attending this webinar. Dave, anything else to add?
No, thank you very much for letting us into your afternoon here for an hour. Appreciate it. Know how valuable your time is. So thank you very much.
Yeah, we hope you found it useful. You'll see a follow-up email after the webinar and a link to the recording. And if any questions occur to you between now and then, be sure to let us know. Thank you all.